Hello, in this video we're going to learn what is a number system, base conversions, and coding representation. So we can start with the module core idea. Module core idea. A number system is a way that's gonna be my screen, and let's try to put it that way. Is a way to represent quantity using a base. A set of digit and position. A set of digit and positional value. Positional value. Computers rely on binary. Computers rely on binary because digital hardware is built around distinguishable physical states. But humans often use decimal, octal, and hexadecimal to read and write values. More conveniently. So that will be the module core idea, what we're going to go through today in this video. A number system is a way to represent quantity using a base, a set of digital and positional value. Computers rely on binary because digital hardware is built around distinguishable physical states, but humans often use decimal, octal, hexadecimal to read and write values more conveniently. Yeah. Let's move on. I'm gonna start with number system. Number system. A number system is a structured method for writing numbers. Using symbols and rules. Using symbols and rules. Okay. A number system is a structured method for writing numbers using symbols and rules. When we write a number, we are not writing marks on a page. We are using a convention. The same quantity can be represented in different systems. For example, the quantity 11 can be written as 11 in decimal, 1011 in binary, 13 in octal, and B in hexadecimal. Okay, so what do we have in here? In here we have like the same quantity can be represented in different systems. For example, 11, we all know 11 like this because it's the system that we are most commonly using, which is decimal, right? But the same quantity, which is 11, can be represented in different, like in binary will be 1011, still 11, in octal will be 13. This is still quantity 11, but represented in different symbol, like different characters for it, right? And it could be in hexadecimal. All of this one, and this one is the quantity of 11, but represented in different systems. That's basically what it says. Okay, let's see the symbol. Let's try to put it more so I have more space in that. The symbol string 11 doesn't always mean 11. In base 10, 11 means 11. In base 2, 11 means 3. We will see that. Can you just, okay. So we have the same quantity. 11 decimal. Okay, we write it like this. When it's in decimal, we don't put 11 and then decimal, because if we have to make every single operation like this, it will be chaotic, right? So how do we represent decimal? Decimal we represent it like this, with a 10 at the bottom, right? Let's try to make it more big and small so we can see clearly the difference. So we have 11 base 10. 11 base 10 mean 11 decimal. So we can say that 11 base 10 is equal to 1011 binary, which is base 2, and is equal to 13 base 8, which is octal, and also is equal to B16, which is hexadecimal. We will see them all later, but right now to get the idea of what are we going through. Every number must be read with its base. The base, yeah, let's copy this too. Every number, basically everything that I'm writing in the billboard, I could just read it through. But the reason why I'm writing it is because if you really want to learn it, that's the only way. Just every explanation that I'm writing has been already summarized and has been already written, and I studied already. There was a big text from the university, and I went through it. I read it. I took the essential, and I'm trying to not abstraction because we're gonna see through everything, but more compact, right? Not just a whole plane of text with most of it could be avoid and nothing will really happen. So everything that I'm just writing is worth to keep it as note. So every number must be read with its base. The base tells us how to interpret the digit. Okay. Oops. One thing to note also is never read 1011 as 1011. If it is binary, it is 1011 base 2 or binary. Okay. Okay, let's check the base or radix. The base, also called radix, tells how many different digit symbols a number system uses before the next place value begins. Basically, we have to go through all the definitions and then we will do with the practice, but it will make sense later. Just if you still don't know how to do it, it also happens to me that I was reading that and I was like, but I don't get it. But as soon as you put it into practice, it really makes sense. So the base, also called as radix, tells how many different digit symbols number system uses before the next really value begins. Okay, base 10 uses 10 digit, uses 10 digits, which is 0 through 9. Base 2 uses 2 digits, 0 and 1. Base 8 uses 8 digit, 0 through 7. Base 16 uses 16 digits, 0 through 9 and A through F. Okay, let's keep moving. In decimal, after 9 comes 10, because we run out of digit. Okay, in decimal after 9 comes 10 because we run out of digit. It's in decimal we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all the numbers that we have, which is 10 numbers because it's base 10. I counting 0 is 10 numbers, but now the number 10 is already this one and this one, so we are just repeating, and then 11 is this one 2 times, so we just run out of digit. That's why we place another position that we will see later. For now, basically what we just write before and this, it means that okay, in decimal system we have 10 digits which go through 0, from 0 through 9. Okay, and after 9 we already run out of digit because there is no more. That's basically the concept of this. That's in decimal. In binary, after 1 comes 10. Because we run out of digit. Or out of single digit, out of single digit much earlier. Okay, much earlier. Let's check. Base 10 we have 10 symbols, which is 0 through 9. Base 2, we have two symbols, which is 0 to 1. Base 8, we have 8 symbols, which is 0 through 7. On base 16, we have 16 symbols, which go from 0 through 9 and from A to F. Okay. In Octal, 8 is not an low digit. In binary, 2 is not an low digit. In hexadecimal, G is not an low digit. Okay, so when we're in octal, this, for example, is not valid. Okay, this is not valid. This, after this, we run out of digit. In hexadecimal, this is not valid. Okay, this is the maximum. We will see that later too. Right now, just get the concept, and then later when you go through the practicals, then you can come back to that and it will make much more sense. Okay, digit set. A digit set is the collection of symbols allowed in a number system. The digit set depends on the base. If a system has base 2, it needs exactly 2-digit symbols. If it has 16 base, it needs 16 symbols. Hexadecimal borrows letters A, B, C, D, E left to represent decimal values, 10, 11, 12, 13, 14, and 15. The hexadecimal number F does not mean the letter F in this context. It means the numeric value 15. Okay. Another thing to check is remember just to not treat A to F as text. When converting hexadecimal. Treat them as numeric digit values. Okay. Positional value. Positional value means a digit has a different value, has a different value depending on its position. In the number. Positional value means a digit has a different value depending on its position in the number. Okay. The rightmost position. These concepts are important because it can avoid to make future mistakes. The rightmost position is the unit's place. Is the unit's place. Moving left, each position is multiplied by the base. In decimal, the places are 1, 10, hundred, and thousand, for example. In binary, they are 1, 2, 4, 8, 16, etc. Same digit. Can therefore represent very different values depending on position and base. Okay, let's take this out so we can put the next example. Okay, in 352 decimal, now we can put the numbers. The 3 means 3 times 100. In 1011 binary, the left most one means 1 times 8. We understand this? So if we check this, I think I have an examples later, but okay, let's carry on, then I will explain that. So base the position, so base 3, base 2, base 1, and base digits multiply their place value. Okay, so this is basically like a number, but the position is 3, number position 2, number position 1, and digits is a digit, and digits multiply their place value, so this digit has to be multiplied by 3, potential 3, because it's his position, his place value. Going back to the example on top, for example, we have 352 decimal, right? 3 means 3 times 100, because this is 300, this is 50, which is 10 times 5, right? That's why 50, and then we have just the unit, which is 2. That's why it's represented like this, and it's going from 10, for example, in this case it was the 300, the unit was 100, from 50 was 10, and for 2 was 1. So the addition of 1 is 2, the addition of 10 is 50, and the addition of 100 is 300. That's what I do want to say. Yeah, this is also good to know, like, do not start powers from the left. The right most position the rightmost digit is always power 0. Okay, so let's start with decimal system. Decimal system the decimal system is a base 10 positional number system that uses the digit 0 through 9. Decimal is the system humans commonly use in daily life. Each place is a power of 10. This is why the number 4382 means 4382 8 tens and 2 ones. Okay, so if we say 4382, it is equal to 4 times 10 power of 3 plus 3 times 10 power is 2 plus 8 times 10 power of 1 plus 2 times 10 power of 0. So we are doing a decimal system. We said that in decimal system we say before we multiply the digit by its base. Okay, so the base is 10 and the digit is 4. So we multiply the digit by its base. This is the digit. This is the digit, right? The digit is 4. The base is 10 because it's decimal. Okay, so this is the base. So we multiply the digit by its base, but in this case the position is 3 because we start always, as we say before, the rightmost position on the rightmost position is power of 0 always. So then it will be power of 1, power of 2, and we finish the last digit, and the last digit in this case finish with the power of 3. So the digit multiplied by its base and power the position. Okay. Okay, let's move on. we can see the example. Here we have 4, 3, 8, and 2, which is 4382. 10 power of 3, 10 power of 2, 10 power of 1, and 10 power of 0. It is 4000 plus 300 plus 80 plus 2, which is the number. Okay. Okay, let's check this table. It's very basic, but it could help us to go through for the next. So we have a decimal place. Then we have the powers of 10, because it's base 10, right? So power of 10. And then the value. Not working. Saying, well, this is okay. So we have 1000, hundreds, tens, and ones. So the thousands is 10 power 3, the hundreds is 10 power 2, the tens is 10 power 1, and the ones is 10 power 0. Every number with power of 0 is always 1. So in here it will be 1110 and 1. This is how the decimal systems work. Let's check binary system. I don't get used to writing this. Binary system, which is base 2. The binary system is a base 2 positional number system that uses only the digit 0 and 1. Binary is crucial in computing because digital circuits can reliably distinguish two categories: such as low, high, off, on, or true, false. The physical states are represented symbolically as 0 and 1. Okay, let's put the example all together. 1011 binary is 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which is equal to 11 decimal. There is two ways of seeing this. Let's move on with the example here. So binary places. To position 7, to position 6. Let me double check this. To position 7, to position 6, to position 5. Okay, to position 7, to position 6, to position 5, to 4, to 3, to 2, to 1, and to 0. Okay, what is exactly this? This is what we need. We do not need to make this one, but we need to know this, so later we can do this. 1, 2, 4, 8, 16, 32, 64, and 128. We are not gonna reach that number, I think, not really often, but I mean, not during this video, but in computational, in future videos, probably yes. But this is the methodology to lead to this table. This is how you position binaries. And now, because we made this, we put all the positions, and now we know this, maybe we can even do this number. Okay, we have in binary 1 0 1 1. Okay, we have 1 2 3 4 positions, 1 2 3 4 positions, 1 2 3 4 positions, and position we have 1 0 1 1. So the 8 is coming, plus in this case is 0 because 0 is, let's say, off, plus 2 is coming, plus 1 is coming because there is a 1, right? 1 0 1 1 1 0 1 1. The only one that is not coming is number 4 because it's 0. If we do this now, 8 plus 2 is 10 plus 1 is 11 decimal, which is exactly this. Okay, let's see. Okay, we can also say that do not say binary is only zeros and ones. Without explaining place value, because the place value give meaning to the zeros and one. Understand? So depending of the position, let's say 1, 2, 4, 8, 16. One in here doesn't is not the same as one in here, okay? Or zero in here is not the same as zero in here. Depending on the position. From physical state to symbols. Low, high, 0, 1, bits, numbers, and text. What it means? It means that you have A, which is 65 base 10, which is equal to 0, 1, 0, 0, 0, 0, 1. The such thing is, yeah, that's the numbering binary of 65 for the binary. And then we have table, which is code system. So basically it means that we have something physical, right? Which is low or high, could be voltage. Then the voltage is gonna be, is gonna take something, and it will be like a value, and it will be represented into binary, which is 0 and 1. And then those 0 and 1 will be represented as bits, and those bits will be represented as numbers that we can read, and then those numbers will be displayed as output. So this is how it works from physical states such as voltage to symbols that we can read. This is the process. Okay. Okay, octal system. Is base 8. The octal system is a base 8 positional number system that uses the digit, that uses the digits 0, let's go 7, octal is useful because one octal digit corresponds exactly 3 binary bits. This make long binary numbers shorter and easier for humans to read. Octal was historically important in computing. Important in computing. And it's still useful and is still useful for understanding permissions and compact binary grouping. Okay, let's move on with examples. Example 1. One, one. So I don't want to give you not an accurate number. 0, 1. Binary can be grouped as 1, 1, 1, 1, 0, 1, which is 7 and 5. I'm gonna put it really separately so you don't confuse and you don't read this as 75. This is 7 and 5. So 1, 1, 1, 1, 0, 1. Wait, let me just double check here. Okay, yeah. Base 2 is equal to 75 octal. Okay, you will get this now, but why did I say that in here I'm gonna put it separately? Because you don't read it at 75, but then the definition is this binary number is literally 75 in octal. The reason is because we are not making the addition of the 75 in its whole, right? We're making the addition of one number plus another number, which is one number plus another number, and then we will connect them together. But we don't go through it as a 75, we will through it at 7 and 5, and then we just put it together as 75 octal. So one octal digit is equal to 3 bits. So 0, 0, 0 is equal to 0. 0, 0, 1 equals 1. Yeah. 0, 1, 0 equals 2. 0, 1, 1 equals 3. 100 is equals 4. 101 is equals 5. 110 is equals 6. And 111 is equal 7. Okay, we can put this as a table. It's gonna be easy to understand. Later go with the other concepts like octal, decimal, and hexadecimal, because all of them share the first, let's say, symbols, the value of the first symbols. That all of them are like, how could I say, like intersection. There is an intersection of all those numbers, so that's why the value is the same. But we will go through it later. It will be easier for us to read some simple binary numbers. Never write 8 or 9 in an octal number. They are not valid octal digits. Okay. Oops. So octal digit, and then 3-bit binary. 0, 1, 2, 3, 4, 5, 6, and 7. We will operate much faster if we can memorize the easy single digits in binary. This is so 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1. No, I think it's right? Let me just double check so I don't give you something. So this is right. That's right. 1, 0, 0, 1, 0, 0, 1, 0, 1, 1. Okay, so that's right. So this is like fastest conversion from octal digits to mapping 3-bit binary, right? Just if you can memorize that, it will save you a lot of time. But I didn't yet, so it's okay. Hexadecimal system. Base 16. The hexadecimal system is a base 16 positional number system that uses the symbol that uses the symbol 0 to 9 and A to F. Hexadecimal is extremely common. In computing. Because one hexadecimal, because one hexadecimal digit correspond exactly to 4 binary bits, to 4 binary bits, long binary numbers, long binary numbers come much easier to read. For example, colors, memory addresses, machine code, and debugging information. Often use hexadecimal. Okay. Example 2, 4, 5, 6, 7. For example, we have one binary which is equal to 1 1 1 1 and 1 1 1 1. So it's equal to f f. So 1 1 1 1 1 binary is equal to f f in base 16. Let's keep with example and then we will see that one x digit is 4 bits. So 0 0. Well, we have the table, look, we're gonna put it anyway. The more that we see it, the better. This is equal 0 0 0 0 1 is equal to 1, and then until 1 0 0 1 equal 9. But then 1 0 1 0 is equal to A. 1 0 1 1 is equal to B. 1 1 0 0 equal to C. 1 1 0 1 is equal to D. 1 1 1 0 is E, and 1 1 1 1 is equal to F. That's why in the example above it is F and F base 16. Like not the whole number, because if we take the whole number as binary itself, it is not F F, it would be different, but because we are making into hexadecimal, we just divide it by 4, and the first 4 So the first four together is we put it like the first group in and the second group is base 16. But there is a way though. For example, so we can see more clear. Let's put 1, 2, 4, 8. Okay, let's put one more just to see. So this is the binary table, and then we have 1, 1, 1, 1, 1. Okay, so if we put these four positions in here, which is one position, another position, another one, and four positions together, then we come these numbers, which is this one is true, this number is true, this number is true, and this number is true. And if we do the addition of this is 12, 14, 15, and 15 decimal, we know it is F in hexadecimal, because in hexadecimal it was uh, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F, which is 10, 11, 12, 13, 14, and 15. So F is 15. And that's why in this case this addition is 15 decimal, but 15 decimal is F in hexadecimal. Okay, we will do the conversions later, but by the time we will do the conversions, I think we already know how to do conversions. But if not, it's gonna be like really difficult to get it if we don't see with examples. So we do the table again. Zero. Oh, let's start with the. Take this out. X digit. Decimal value. And 4-bit binary. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Actually, let's take this out. Okay, 0 is 0. In binary is 0, 0, 0, 0. Number 1 is 1. Number 2 is 2. Number 3 is gonna be 3. Number 4 is gonna be 4. The 5 is gonna be 5. 6, 7, 8, 9, 10, 11, 12, 13. Doesn't look really good, right? Let's make it the table. Let's make it clear. It's a very simple concept, but there is no need to do it that way. Let's just go through it as we saw. 4-bit binary. Okay. Should not take a lot of time, but let's make it right one. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Still, I think it's better than before. Not much better, but better. That one is not gonna work. Okay, I think we get it. Do we? Yeah. I could use the rule though, but I think we will save time that way. Oops. Okay, we don't need it for that. Okay, in decimal value, the hexadecimal digit will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. From here, all of them matches, right? Because hexadecimal, decimal, and octal from 0 to 7, all the symbols has the same value. Okay, in hexadecimal from 0 to 9, in decimal value from 0 to 9, and in octal from 0 to 7. So in all of them, because octal is 0 to 7, we don't count binary because binary is after 1, right? So in those three, like hexadecimal, decimal, and octal, because octal is the shortest one, is the first one to run out of digit of those three, because it's from 0 to 7, all of them until the symbol 7, the value matches. In this case now is 10, 11, 12, 13, 14, and 15. So if we are mapping into 4 digits, it will be 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. It will be like this. Let me double check. 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1. Okay, all of them are correct. Okay, so that's the table from hexadecimal to decimal, and then for mapping for bits binary. Again, if you can memorize that, you will save time. If not, it's not also like so complicated just to locate all the positions in binary and just go through it. But if you memorize it, it saves time. Okay, we can do the comparison table. Okay, let's do this as a summary, and then we can start with the conversions. Okay. Comparison table. Decimal, binary, octal, and hexadecimal. This table is one of the most important visual summaries for the class. Okay. System. Base. Allow digits. Place values. And why it matters. Actually, we can just go through it very quick because the way that we did the video so far, we explain it. We can just say decimal is base 10 and it's go from 0 to 9. Binary is base 2 and it go from 0 to 1. Octal is base 8 and it go from 0 to 7. And hexadecimal is base 16 and it go from 0 to 9 and from A to F. Okay, I'm gonna put that. Okay, let's move on. That's gonna make it like a bit confusing, and we're gonna see the conversions now, so it makes sense later. Okay, so we can say why computers use binary. Computers use binary because real hardware can more reliably distinguish two categories. The many subtle categories. A voltage can be treated. Voltage can be treated as low or high. A switch can be off or on. A memory cell can be interpreted as storing 0 or 1. So this doesn't mean computers literally think in human symbols. It's mean the physical machine is organized. So certain physical states are interpreted as binary values. As binary values. Okay. So we have physical hardware states, which can be low voltage and high voltage. It could be represented 0, it could be represented 1. So some categories make digital systems reliable. Okay, let's move on. Okay, let's go through conversions. The idea of conversions. Conversions is the skill of translating the same value from one representation system to another. Coding representation, coding representation is the skill of understanding how symbols such as letters, decimal digits, and text characters are represented with binary patterns. Okay. Okay, so let's see how to convert values between decimal, binary, octal, and hexadecimal. Okay. Okay, let's start with a table that will make no sense at all right now. But as soon as you get into the practice and you go back to the table, it will make sense a lot. Okay, conversion map. It's good to have this table so we can rely into something after the practice. Conversion map. The fastest way to understand base conversion, a base conversion is to see that there are two big families of methods. Place value, expansion, and repeated division. For binary, octal, x, grouping bits is the easiest method. Okay, the fastest way to understand base conversion is to see that there are two big families of method: place value expansion and repeated division. But for binary, octal, and hexadecimal, grouping bits is the easiest method. Okay, let's put conversion. We can put binary to decimal. Let's put more. decimal to binary, binary to octal, octal to binary, binary to x, x to binary, decimal to octal, x. Okay. Let's do that. Gonna be easier. Let's put the best beginner method. In this case is place value expansion. Right now just copy the table, and then once we put this table into practice, it will start to make a lot of sense. And here is repeated value division by 2, repeated division by 2. Binary total is group bits, is to group bits by 3 from the right. Replace each octal digit with 3 bits. Okay, replace each octal digit with 3 bits. Okay. Binary to x groups bit by 4 from the right. And here is again replace each digit x digit with 4 bits. And here is a repeated division by 8 or 16. The key idea to multiply each bit by its power of 2 and up. Okay, here is divide by 2 and read reminders, bottom up. Okay, each 3 digit, each 3. Now we are in binary octal. Is 3-bit group. Not sure if I can delete this without. Oops, yeah. Okay. We're in here. Okay, fix it. Each 3-bit group becomes one octal digit. I know, what are we doing? We didn't fix it. Okay. Now we have it. Okay. Sorry about that. Now we have 3 digits. It's 3 bits. Map and 3 group. This is a group. Becomes one octal digit. This is where binary octal is one octal digit. Now we are fine. One octal digit. Okay. Now in octal binary, each octal digit, each octal digit has a fixed 3 bits pattern. 3 bits pattern. Okay. Now binary hexadecimal, each 4-bit group becomes one hex digit. Okay, each digit has a fixed 4-bit pattern. And here is divide by the target. Base and read reminders. Bottom up. Okay, that took some time, but it's really good if you have this table, because after you do some practice, then we start with some exercises, you will see that this table will be really easy to read, and also if with time, because you go to a different material, you are kind of forgetting how to do it, because you already knew how to do it. Just by reading this table you get back to it, so it's really good to have it. It took a long time. Okay, let's start. Binary, let's put them on top so we have more space. binary to decimal. Okay, place value method is place value method. Okay, to convert binary to decimal, write the powers of 2 not above the bits, write the powers of 2. Let's put it just like this. Then multiply each bit by its place value and add the results. Okay, so we have an example which is convert 1011 binary to decimal. Okay, we have the binary which is 1011 place value which is 8421, right? Remember the place value for binary, it's power of 2, 8, 16, 32, 64. Let's make it more. Okay, 1011. Now the place value is 8421. Okay, now multiply which is 1 times 8 0 times 4 plus 2 times 1 plus 2 times 1. Okay, and now the answer, which is 11 decimal, because 1 times 8 is 8 plus 0 plus 2 is 2 plus 1, which is 8 plus 2 is 10 plus 1, 11 decimal. So the answer is 11 decimal. You can do like we did before, right? We can say like on and off, but just you can multiply like this too, which is the same result. Okay, let's see some other examples. Binary place value expansion decimal. Okay, so let's say 110. 11001 binary. One zero 1101 binary. How many positions? Zero. One, one, okay. Let's put this. Okay. So for the place value expansion, we have to put the table for binary that we already know. Okay, so one. Let's try to make it more space. How many? It's 1, 2, 3, 4, 5. Okay, so it's 2, 4, 8, 16. Okay. So now we got the numbers on the left. So we have 1, the first one. We have the position from the right and the position from the left. So we can start from here. So 1 times 16 plus, next one is 1. 1 times 8 plus the next one is 0, right? So 0 times 4 plus the next one is another 0. 0 times 2 plus the last one is 1. 1 times 1. If we make this, let's do it and then we can so it's 16 plus 8 plus 0 plus 0 plus 1, which is 25. Yeah, so 25 decimal. Okay, let's do the same here. So we have positions 2, 4, 8, 16 and 32, and we have the numbers 1 times 32 plus 0 times 16 plus 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, and it will give you 45 decimal. Okay, and the last one we only have all ones, so we can go straight and say, okay, the values in here, we counted there 8 values. So 1, 2, 4, 8, 16, 32, 64, 128. That will cover all the position for its number, but we can, as we saw above, is 1 times 32 is 32, 1 times 8 is 8, and here we only have 1, so we can already just do the additions of it, because the multiplication of every digit will be same as the factor, right? So we can say just the total addition of that is 255 decimal. Okay, let's do decimal to binary. Decimal to binary. We're gonna use the repeated division method. Okay. To convert decimal to binary, starting to give me those problems. I don't know why if I put it back in and then I just take it back again, it starts to work for no reasons. To convert decimal to binary, repeatedly divide the decimal number by 2. Write the remainder each time when the quotient reaches 0. Read the reminders from bottom to top. Okay, so example. Convert 25 decimal to binary. Okay, so we have 25 divided by 2 is equal to 12. Remainder 1. Why is equal to 12 remainder 1? Because 25 by 2 is not the exactly number, right? In this case it will be 12.5. So this 0.5 gives us a remainder of 1. Okay, because 0.5 times 2 is 1. So it gives us a remainder of 1. So 12 now divided by 2 is equal to 6, but this is exactly. So the remainder is 0. And now we have 6 divided by 2, which is exactly 3, and the remainder again is 0. Remainder is 0. Now we have 3 divided by 2, which is 1, and in this case the remainder is 1 because it's not exactly. There is a 0.5 in between. 0.5 times 2 is 1. And now we have 1 divided by 2, which is 0, and the remainder is again 1 because it's not precisely 0.5, right? Okay, now we read reminders from bottom to top. From bottom to top it gives 1, 1, 0, 0, 1. So we are converting 25 decimals, so we can say that 25 decimal is equal to 1, 1, 0, 0, 1 binary. Okay, let's do some more examples. Let's convert 45 decimal to binary. Okay, 45 times 2 is equal to 22. Reminder 1. Now 22 times 2 is equal to 11. Reminder 0. Now 11 divided by 2 is equal to 5. Reminder 1. Now we have 5 divided by 2 is 2, but reminder again is 1. Now we have 2 divided by 2, which is 1, and the remainder in here is 0 because it's exactly remainder is 0. And now we have 1 divided by 2, and again this is a 0 with remainder of 1. Okay, and now we read number from bottom to top. So we have 1, 0, 1, 1, 0, 1 binary. So we can say that 45 decimal is equal to 1, 0, 1, 1, 0, 1 binary. Okay, let's do another example. Let's convert 156 decimal to binary. We do the same. 156 divided by 2 is equal to 78. Remainder 0. 78 divided by 2 is equal to 39. Remainder 0. 39 divided by 2 is equal to 19. Remainder 1. 19 divided by 2 is equal to 9. Remainder 1. 9 divided by 2 is equal to 4. Remainder 1. 4. 4 divided by 2 is equal to 2. Remainder 0. Reminder 0 2 divided by 2 is equal to 1. Reminder 0 and 1 divided by 2 is equal to 0. Reminder 1. So if we read from bottom to top, we have 1 0 0 1 1 1 0 0 binary. So 156 decimal is equal to 10011100 binary. Okay. We can use the shortcut method subtracting powers too, but this is a bit more confused. Let's skip that one. Let's do binary to octal. Binary to octal, which is grouping by 3 bits. By 3 bits. Okay. We can say because 8 is equal to 2 power of 3, one octal digit matches exactly 3 binary units. 3 binary units. To convert binary to octal, group bits from the right in group of 3. In group of 3. At leading zeros, let's put this because this is important and I don't want to make confused. So at leading zeros on the left if needed. Okay. We will see the example now. Is just for matching the groups. example, convert 1 1 0 1 0 1 0 1 1 1 binary to octal. Okay, now we group from the right in 3 bits group in 3 bits group. Okay, so we have the number which is 1 1 0 1 0 1 1 1. So we said that we're gonna group from the right in 3 bits group. Okay, let's start with the rights. We have 1 1 1. Let's take another 3. We have 0 1 0. Let's take these 2 1 1, but one is missing, right? This one is missing, and it's in here, add leading zeros on the left if needed. We need another zero, so we put another one, and now we have 1 2 and 3 different groups. And now we do the conversions, like 1 0 1 1 is equal to 3, 0 1 0 is equal to 2, and 1 1 1 is equal to 7. We will know this by heart if we will have memorized the table, but we didn't memorize the table. So let's do it quickly. 1 2 4 8 16. We have 0 1 1, first one, this one. Okay, 0 1 1, the 4 commas. If we do it with the times, we can say that 0 times 4, or in this case will be 4 times 0 plus 2 times 1 plus 1 times 1. So it will be 4 plus 2 plus, oh, the series, I was confused, I was like, what? Okay, this is 0 plus 2 plus 1, which is equal to 3. So this is equal to 3. We put it in here, is equal to 3. Because we are mapping in Octal, we are mapping by 3, and in hexadecimal we are mapping by 4. So single digit mapping by 3 and mapping by 4, this here will always be true. So you can always do that. If you are mapping 3 or mapping 4, you can always use this one, which is the easiest one, the fastest one, and will always be true. Okay, let's do 1 2 4 8. We have 0 1 0. So this is 0, this is like 2, and this is 0. So it's gonna be 2, right? Because we do addition is 2. Okay, now we do 1 1 1 1. So 4 times 1 plus 2 times 1 plus 1 times 1 is 4 plus 2 plus 1 6 plus 1 7, which is down. So 1 1 is equal to 7, which is down. Okay, let's move on. Oh, but we did finish the example though. Okay. Let's put it back again. The example was to convert 110.111 binary to octal, right? To octal, and then we put it on groups of 3, which is let's do it again. 110.10111. In groups of 3 it was 111. This 3, now this 3, 0 1 0, but now this is only 2 1 1, and we could add a 0 on the left if we wanted, just to, if we needed to match the back of the group of 3, right? Okay, and now we can say that 0 1 1 was equal to 3, 0 1 0 was equal to 2, and 1 1 1 is equal to 7. We saw the conversions, right? And now we say the 1 1 0 1 0 1 1 1 binary is equal to 327 octal. Okay, in this case we don't count from bottom to top. In this case is because we are not doing like, this is not like the divisions, right? And then the reminders from bottom to top, remember that? In this case we are just taking values. There's one value, there's another value, there's a third value, and we just put them together. We paste it all together. 327 octal. Okay. Octal to binary. Replace each digit with 3 bits. Okay. To convert octal to binary, replace every octal digit with its 3 bits, binary equivalent. Okay, let's see an example. So to convert octal to binary, replace every octal digit with its 3 bits binary equivalent. So let's put the example. We want to convert 75 octal to binary. Okay, then if we know the table, we know that 7 is 1 1 1 and 5 is 1 0 1. Someday we can put them together and say that 75 octal is equal to 1 1 1 plus 1 0 1 binary. Okay, this plus this all together like a text. It's like concatenating text. Okay, and let's say that we don't know. Let's say that we don't know this still. Okay, so we do it 1 2 4 8 16. There is three numbers. We have 7. In this case, okay, in this case is different because in this case we don't have this already, right? We just put this because we know this from the table, but we don't know now. We have to convert 75 octal to binary. We have the 7, we have the 5. And we know that to convert octal to binary, replace every octal digit with its 3 bits binary equivalent. So we know that we need 3 bits binary, and we have this number, a 7 and a 5. How do we do it? Okay, we go to the table, which is this one. Okay, we go to this table. And what do we see in those positions? We see that 16. We put, you can put 20 positions, you can put many positions as you want, but all of things from the left will be worthless because, for example, we see the 16 and we want 7. We want the value of 7, but 16 is already greater than 7, so we cannot use 16. What about 8? It's still greater than 7. We cannot use 8, but we can use the 4. The 4 we can use it because it's less than 7. So we put the 4. What else can we use? Can we use the 2? We can use the 2 because we still have margin, right? 4 plus 2 is 6, not 7 yet. So we can use that. Can we use the 1? Yes, we still can use the 1 because we still have margin. So we have this. 4 plus 2 is 6, plus 1 is 7. So we have the 7, and we have the 1 1 1. Okay, and we already know that this 7, it doesn't matter if this 7 is octal or if this 7 is decimal, or even if this 7 is hexadecimal, because until 7 all of them matches, all the same symbol match the quantity. Okay, let's do with the 5. Now we want to know the number in 5. 8 is greater than 5, so we cannot use it, but we can use 4. So we put 4 plus. Can we use 2? No, because 4 plus 2 is already 6, which is greater than 5. So we cannot count 0. We cannot count 2, so we put 0. Plus, we can count 1, because 4 plus 1 is 5, which is the number we want to get. So if we do 4 plus 0 plus 1, it is 5. And here on top, we got the binary number, which is 1 0 1. And now, if we put it together, we already knew this one. This one is 75 octal is equal to the 7, which is 1 1 1, and the 5, which is 1 0 1 binary. Okay, it's important to know that every single time you are mapping by 3 and by 4 single digit, this will always be true, but this will always be true if you are grouping bits. because this is right now true because it's 7 and 5. It's not 75 itself. If it will be 75 itself, this number will be different. This number here will not be 75 at its whole, will be a different number. But because we are mapping and grouping, we are just adding 7 and 5, and this is how Octal works in the conversion, then we can do this one, and this one will always be true because we are mapping 3 in Octal and 4 in hexadecimal. Okay, but this is not 75, this is 7. This is like concatenating the text 7 with the text 5, and then we have here the text 75. It's not text, but just to uh, make it like, try to make it sense, like it's just like concatenating. Okay. Okay, we can put octal digit and 3-bit binary. We have already seen this like 5 times already, but the more we see, the better. 6 and 7. This will be 0, 0, 0. This will be 0, 0, 1, 0, 1, 0, and 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, yeah, and 1, 1, 1. Okay. Let's do binary to hexadecimal. Binary to hexadecimal. And it's grouping bits. Grouping. Let's put grouping by 4 bits. Okay. Because 16 is equal to 2 powers of 4, 1 hexadecimal, 1 hexadecimal digit matches exactly 4 binary bits. To convert binary to hexadecimal, group bits from the right in groups of 4, in groups of 4, and then the same at leading zeros on the left if needed. Okay, it's like the octal but 1 extra bit. Let's put this in charge. Okay, example. Convert 110 101 . 1 1 0 1 0 1 1 1 1 binary to hexadecimal. Okay, first thing we do, we group from the right in 4 bits groups. Okay, so we have the whole number, which is 1 1 0 1 0 1 1 1. So we can take the first 4, which is 0 1 1 1, and another group of 4, which is 1 0 1 1. Okay, so we have 2 different groups of 4, and now we can say, let's take this out, let's make some more space here. 0 1 1 1. Okay, and now by the conversion tables we know that 1101 is equal to d because we are in hexadecimal, and 0111 is equal to 7. Okay, but we don't know. Let's guess that we don't know. We do exactly the same. 1 2 4 8 16. No. In this case we have the, let's say that we don't have this, but we have the binary numbers that make it even easier. 1 1 0 1, we have 4 positions, the last 4 positions, which is 1 1 0 1. What it means? It means that we can count 8 plus 4 plus 0 plus 1. What does it say? It says 8 is 10 12 13. Okay, so we have, this is 13, but we are in hexadecimal. Hexadecimal has no 13. Hexadecimal is 0 1 2 3 4 5 6 7 8 9, A B C D E and F. That's the hexadecimal. But in hexadecimal, this represents 10, this 11, this 12, this 13, this 14, and this 15. So we have 13, and 13 represents D. So this is D, which is equivalent to 13 in decimal. Okay, let's move on. Now what do we have? We have 0 1 1 1. Okay, 0 times 8 is 0, right? So we don't even count it. So we have 4 plus 2 plus 1, which is 6 plus 1 7. So this is 7. Okay, and now what we do here, exactly the same that we did with the octal. We have this value, which is this one, and this value, which is this one. So that will be D, and this will be 7, right? And what are we converting to hexadecimal? We are converting the number, this number, which is 1 1 0 1 0 1 1 1 binary. We can say that is equal to D7 hexadecimal. We get it? Okay. Let's do now hexadecimal to binary. hexadecimal. Let's try to write hexadecimal. Hexadecimal to binary, which is replace each digit with 4 bits. Okay. To convert hexadecimal to binary, to convert hexadecimal to binary, replace every x digit with its 4 bits binary equivalent. Okay, let's go through it. Example, we are going to convert to f hexadecimal to binary. We know that 2 is equal to 0, 0, 1, 0. And f is equal to 1, 1, 1, 1. But again, let's see, we don't know. Let's go through it. How can we solve this? 2, 4, 8, 16. Okay, and we have 2. We know the 2 is 2 in every single number system, right? So, but we're mapping 4 in this case. So we have to take 4 position because we have to, let's do it step by step. 2. 4 is greater than 2. We cannot take 4, right? So we take 2. And it gives 2. Can we take 1? If we take 1, it will be greater than 2 already, so we can also not take 1. So it will be plus 0. This is 2. But we have only 2 positions, which is 1 and 0. And if you remember, in the grouping bits, hexadecimal, it said that we can add leading zeros on the left in order to group the 4 the 4 bits, right? In octal was 3, in hexadecimal is 4. So we know that we cannot take 4. And we know that we cannot take 8. And now we got 4 bits. 0, 0, 1, 0, 0, 0, 1, 0. Okay? Let's do F. What is F? The only thing that we know in F right now is that F is a hexadecimal number. That's the only thing that we know so far. Okay, let's do the table. 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And we know that this is 10, 11, 12, 13, 14, 15. So F is 15. Now we know that F hexadecimal is equal to 15 in decimal, right? And now we can work with that. Again, we need 4 because we are grouping in 4 in order to convert from hexadecimal to binary. So 16, can we take 16? Is already 16 is greater than 15, so we cannot take it with put 0. Can we take 8? Yes, 8 we can take it. Plus, can we take 4? Plus 4 is 12, so we still can take it. plus, okay, now we have 8, 10, 12. Can we take 2? Yeah, if we take 2 is 14, it's still not greater than 15. Oh, sorry, it's still not greater than 14, than 15. Can we take 1? Yes, if we take 1 now, it is the total addition of 15. And we have to take 4 in order to group. So we take 4. And we can say the f in hexadecimal, which is the same as 15 in decimal, and we saw the 15 in decimal is equal to 1, 1, 1. So 1, 1, 1, 1. What can we say now? We can say that 2f 16 is equal to 0, 0, 1, 0, and 1, 1, 1, 1 binary. Okay, and these two zeros on the left, we can say that usually we can drop leading zeros and say that 2f hexadecimal is equal to 101111 binary. Okay, okay, let's see decimal to octal. Decimal to octal. Repeated division by 8. To convert decimal to octal, just the same, use the same repeated division method, but divide by 8 instead of 2. Read the reminders from bottom to top. Okay, let's do an example. Convert 156 decimal to octal. Okay, so we have 156 divided by 8, which is equal to 19. Remainder of 4. Okay, I will explain the reminders now. Let's carry on. Now we have 19 divided by 8, which is 2, remainder 3. And then we have 2 divided by 8, which is 0. Oh, this happened again. Seems like he has some kind of like battery in it or something. I don't know, man. It is equal to 0 reminder 2. Okay, what about the reminder? What if we don't know how to take the reminders? So we have a division which is 156 divided by 8, and we say that it was 19, but with the reminder of 4. Okay, so what exactly mean this? It means that in a group of 19 we can do 8 groups of 19 and will give us 156, but this is not accurate, right? Because 19 is not accurate, it will be 19.5, and now this 8 groups of this will be 156. Okay, we have this, but we didn't do anything with the reminder. But if we multiply the reminder and we put like so here, and we multiply the reminder and we say, okay, 0.5 times 8 is equal to 4. So 0.5 times 8 is equal to 4, and that's the remainder of 4. Let's do the other example. Now we have 19 divided by 8, and we say that this is 2, but the remainder of 3. Okay, because it's 2.5. And then this 0.5, this 0.5 per 8, no, something's wrong here. Let me double check. We said that this is 2, remainder 3. Okay, okay, because that was not exactly there. 37. That's also not exactly there, but more often. Okay, in this case we do the division, which is 19 divided by 8 is 2.37, and if we do the 37 times 8, it gives us the approximation of 3, remainder 3. Or if we take it completely, maybe it will give us, let's take it completely. Let's say 19 divided by 8, 375 is the decimal. 375 times 8 is equal to 3, exactly, yeah, that was the case. Okay, so in this case this division is 2, 3, 7, 5. So if we do the 375 times 8, it gives us the remainder of 3, exactly the same that we did on top. Okay, resolve now. Let's do now the last one so we can do all of them now. Okay, it's 2 divided by 8, that will give us 0, remainder of 2. And to give us a remainder of 2, it could be 0.5. 0.25, sorry, 25 times 8 is 2, exactly. So that was like by editing. So 25 and 25 times 8 is 2. Yeah, that's what we said, right? Yep. Okay. So that's the reminder of that one. Because this is 0.25, so it's 0, right? And now we take the 0.25 times 8 and it gives us 2, and that's the reminder. Okay. Something simple, but after. Can we go back one? One? Yeah. Something simple, but after like 3 4 hours already, it's like some concepts. It's not. Okay. We didn't finish that. We just saw the reminders. And now from bottom, read from bottom to top, which is 2, 3, and 4. So 156 decimals is equal to 234 octal. That's the conversion. Okay. Still recording. Okay. Let's do decimal to hexadecimal. Decimal to hexadecimal. Just repeat it. Division by 16. To convert decimal to hexadecimal, repeatedly divide by 16. Reminders. Ten through 15 become A through F. It's something that we already know, right? Okay. Example. Convert 156 decimal to hexadecimal. Why is this failing now? To hexadecimal. Okay. So 156 divided by, no, it's confused now. Yes, we're in base 16. Divided by 16 is equal to 9. Reminder 12. So in here, we already know how to take the reminders. We did it before, right? But one extra thing in here is 12. 12 is not an allowed digit in hexadecimal. So 12, if we do again the table, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And A is 11, is 10, 11, 12, 13, 14, and 15. We know that 12 is C. So this is equal to C. And we keep is 9 divided by 16 is equal to 0. Remainder 9. So 156 decimal is equal to 9C decimal. Because we don't put the 12, we put C, and we read from bottom to top. So 156 decimal is 9C hexadecimal. Okay? Okay, let's do octal and hexadecimal. To decimal with the place value expansion. Okay. To convert octal or hexadecimal, octal or hexadecimal to decimal, use the same place value. That doesn't help a lot. I don't know what is he feeling like this though. It's pretty bad. Take it out again. It's already difficult to write in here. Imagine if you make it even more complicated. Place value rule, which is digit times the base with power position. Okay, this is the formula. It's a digit times base with position power. Okay, example. Let's say an octal example first. Octal example. Convert 234 octal to decimal. So 234 octal is equal to, we have three numbers, so three positions, right? Is equal to 2. We have a digit, which is, the digit is 2 times 8, which is the base. We are in octal. In octal is base 8, but the power of the position in this case is 2, because we already saw in the beginning that the rightmost position on the left is always rightmost position on the right is always the power of 0. So it will be 2 now plus the digit times the base 1 plus the digit times the base position 0, because the rightmost position is 0 on the power. Okay, and we can say that this is equal to 64. Sorry, it's 2 times 64 plus 3 times 8 plus 4 times 1, because every number with the power of 0 is 1. Okay, and now we can say that 128 plus 24 plus 4, which is equal to 156 decimal. Okay, okay, let's do an hexadecimal example. Example. Convert 9C hexadecimal to decimal. Okay, we have 9C hexadecimal, which is 9, the digit, times the base. Now we are in base 16. On the power of the position, we have two positions. Counting with the 0, that will be the rightmost, then this. Okay, my phone, turn it off. We were checking an example with hexadecimal. Convert 9C hexadecimal to decimal. Okay, we saw 9C hexadecimal is equal to 9 times 16. Okay, the digit. Okay, we're here. The digit times the base, so which is 9 times 16. And power position, in this case there is two numbers, so two positions, right? So we start with position 1 and then plus, now is 3 times the base 16 and position 0, and we know the C is equal to 12, so this is equal to 9 times 16 plus 12 times 16. No, sorry, 12 times 1, because every number power to 0 is 1. And this is equal 144 plus 12, which is equal to 156 decimal. Okay, okay, this one, let's put this table. Okay, conversion summary table. Conversion summary table. So we can say start. We can put put binary, decimal, binary, octal, binary, x, and then decimal, and decimal. Okay, let's do this. Okay, let's put target. This is gonna be decimal, binary, octal, binary, X, binary, octal, and X. The method, some power of 2 divide by 2 let's try. Reminders upward. Okay. Group of 3 bits from right. In octal binary, each octal digit, each octal digit, 3 bits. In binary, X groups of 4 bits from right, groups of 4 bits from right. I hope it's understandable because it's really difficult to write in here, and the problem is I'm gonna be somewhere here. I'm gonna put someone in my face recording, so I don't know how much position will take in that. But groups of 4 bits from right, I think is difficult to understand but understandable. X binary is X digit. I don't have much space. 4 bits. Decimal octal is divide by 8. Divide by 8. Read reminders. Upward. Divide by 16. Divide by 16. Map 10, 15 to A F. Okay. An example result. 1011 binary equal to 11 decimal 25 decimal equal to 11001 binary. Decimal to binary, divide by 2, read reminders about. This is understandable, yeah. 1, 2, 3, 4, 1, 1, 1, 1, 0, 1. Binary is equal to 75 octal. Binary to octal, yeah, no example. Octal binary 75 octal is equal to 1, 1, 1, 1, 0, 1 binary. Binary x 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1 binary is equal to the 7 hexadecimal, and then the same the 7 hexadecimal is equal to 1, 1, 0, 1, 0, 1, 1 binary. 156 decimal is equal to 234. I think those examples that I have in this table are the examples that we saw in previously exercises, so you can check the previously exercises and then come back to the table just as a summary if you need it. 156 decimal is equal to 90 hexadecimal. Okay, so binary to decimal with some power of 2. And we're finding there. Okay, decimal binary is divided by 2 and read remainder upwards. Binary to octal group of 3 from right. Yeah, it's understandable. Okay, every table helps. So if I will be someone who want to learn this from the beginning, I will take this table, all the tables that I'm writing in here that I have in the example that I'm explaining of is all the tables that I also took myself from the university. So there was many tables that I didn't do, but they were just explaining the same. Even some of the tables that we're using are basically like almost the same as the other ones, but the tiny difference. Okay, let's check coding representation. ASCII Unicode BCD gray code and F set dick. Okay. Okay, we can say the number systems explain how quantities can be represented coding system explain how symbols characters decimal digits or special knockout sequences can be presented using binary patterns. Okay. For example, the binary number 0, 1, 0, 0, 0, 0, 0, 1 can be interpreted in different ways. Depending on the code. In ASCII, it represents the character A as an unsigned binary number. It represents decimal 65. So meaning depends on interpretation. Okay. So binary pattern zero one 0, 0, 0, 0, 0, 0, 1 as unsigned number is equal to 65 as the character is A. So it's same bit but different interpretation. Okay. Let's check if we can do this. Just one 2, 4, 8, 16, 32, and 64. Plus 64 and 128. Yeah. Okay, so we have. No, it's gonna be that. So we have this number. Okay, so we want to check this number. We can say here 1, 0, 0, 0, 1, 2, 3, 4, and 5 zeros. 1, 2, 3, 4, 5 zeros. And then 1. Okay. Because let's say that we don't know if it's 65, right? Because if we know already it's 65, we can start for 128 is higher than 65, which already, so we start with the 64. In this case 64, it's lower, it's less than 65, so it counts. So 64 plus, can we add 34? No, because then it will be greater than 65, plus 16 will still be greater than 65, so it doesn't count. 8 doesn't count, still greater. 4 is still greater. 2 will be still greater because 64 plus 2 is 67. 66, sorry, but still greater than 65. But plus 1, 64 plus 1 is 65, so plus 1 is working. So if we do the addition of this one with this one is 65. So we know that this number, this number, if it's not like it says in here as an unsigned number, if it's not in ASCII, then this number 65 will have this number in binary, but in ASCII it's represented as a. Okay, so it will only be a if it's the system tells you is represented as a, because we're using the system called ASCII. Okay. Let's check what is ASCII. ASCII. So definition. ASCII. Oops, goes down. Ay, ay, ay. ASCII. ASCII is a character encoding system. The maps common English letter, digit, punctuation, and control characters to numeric codes. ASCII originally uses 7 bits, giving 128 possible codes. Computers can store the code as binary. For example, uppercase A has a decimal code 65, which is 0 1 0 0 0 0 0 1 binary in 8 bits binary form. Okay. More or less, we are getting what exactly ASCII is. For example, is the key, right, in the keyboard. The A, every single time you press A, uppercase A. In ASCII, this is how it's represented by the computer with this binary number. So it's just mapping the text hey hi can be represented as H, which is equal to 72, and I, which is equal to 73, which become binary patterns stored in memory. Okay. So we have a unique character numeric code and binary, which is a 65 decimal, and then it will be 0 1 0 0 0 0 0 1 binary. Okay. We have also, for example, B, which is 66 decimal, and then it is 0 1 0 0 0 0 0 1 0 binary. Okay, we more or less understand this. Okay, let's say do not confuse the character 1 with the number 1. in ASCII, the character 1 has code 49, not numeric value 1. Okay, you can say character A B A 0 1 space okay, ASCII decimal. This is 65, 66, 97, 48, 49, and 32. In 8-bit binary, it is 0, 1, 0, 0, 0, 0, 1. Let me yes. I did it wrong before. 0, 1, 0, 0, 0, 0, 1, 0. I think I put 5 0 in the last example. Okay. 97 is 0, 1, 1, 0, 0, 0, 0, 1. I'm just counting the 0 because don't want to give you the wrong data. 0, 0, 11, 0, 0, 0, 0, and it's 0, 0, 11, 0, 0, 0, 1, and for 32 is 0, 0, 1, 2, 3, 4, and 5, 1, 2, 3, 4, and 5. Okay, that will be crazy to memorize all, but it depends, right? If you're gonna work long, like you're pretty sure the ASCII is the only encoding system that you want to use, then yeah, just go for it. But if not, I guess we will have to come back to the table every single time. Okay. Now the alarm went on. Where were we? Okay, we finished with this example. There's too many things happening while recording this video. The phone turned off, the laptop turned it off, the alarm take the video off. It's getting too long. Unicode. Everything is recording, right? Yeah, okay. Unicode is a universal character. Standard designed to represent characters from many writing systems and symbols around the world. And symbols around the world. Okay. We can say that ASCII is limited for global text. Unicode assigns code points such as U plus 0041 for A and U plus 20 AC for the euro sign. Encoding such as UTF-8 stores those code points as bytes. And this allows computers to represent Spanish accent, German umlauts, emojis, mathematical symbols, and many world languages. Okay. The character this character ñ is called this Spanish character is not part of Project 7-bit ASCII, but it is representable in Unicode. So we get the idea, right? The difference between Unicode and ASCII. example, human text like A, and you unload the euro signs of this special character. Unicode points, Unicode code points like U plus 0041, U plus 00F1, U plus 00FC, U plus 20AC, etc. Okay. Unicode is the standard. UTF-8 is one common way. Is one common way to encode Unicode into bytes. So they are related, but not identical concepts. Okay. Let's check B, C, D, which is binary coded decimal. Okay, B, C, D represent each decimal digit separately using a 4-bit binary pattern. In normal binary, the decimal number 59 is represented as 111011 binary in B, C, D. The decimal digits are encoded separately. For example, 5 becomes 0 1 0 1, and 9 becomes 1 0 0 1. So 59 becomes 0 1 0 1 1 0 0 1, and this is useful when exact decimals decimal digit representation matters, such as display, or financial decimal handling. Okay. Let's see more of it. 59 base 10 in BCD is 0 1 0 1 1 0 0 1, but 0 1 0 1 1 0 0 1 as a normal binary number is equals to 89 base 10. So context matters. Okay. This is what I explained it before. Let's see if with the example we see clearly. If not, I explain it before. Decimal number 59. Normal binary 1 1 1 0 1 1. In BCD 5 is equal to 0 1 0 1, and 9 is equal to 1 0 0 1. So in BCD result 0 1 0 1 and 1 0 0 1 will be 59. This is equal to 59, but only in BCD. In normal binary is different. Let's see. If we can check. Okay. let's try a normal binary first. Okay, we can do 1 2 4 8 16 32 64. Okay, it's already higher than 59, so we can get 32. Can we get 16? Yes, still we can get 16. Plus, can we get 8? We are talking about, that will be 38, 48, 48, 52. Yeah, we still can get 8. Now we will have 38, 48, 50, 52. We are doing this one normal binary now. Okay, we are doing the normal binary. 38, 48. This one doesn't work because we already has, so that will be 0 plus, we can take 2 more and we can take the last one, and if we do the addition of this, it will be 38 plus 16 is 38, 48 is 48, 58, 58. Not that pass now. Am I able to do addition? Did I did it wrong? 38, 48, because I'm doing in 3 different languages. I'm gonna try just to focus on one. Okay, yeah. The total addition of this is 59. Okay. I'm faster doing addition in Spain than in English, which is obviously is my mother language, but okay. So this one, 1 1 1 0 1 1. This is the normal binary number. Okay, but we are doing a different one. We are doing BCD. We want the BCD results, and in BCD results is mapping 4 bits, right? And taking 5 and then 9 and then paste it together like we saw earlier. Okay, so for 5 we cannot take 0, we cannot take 8, but we need 4. So this is 0 plus 4 plus 2 is already higher than the 5, so 0 plus the 1, and that will be 5, which is 0 1 0 1, which is 0 1 0 1. We do the same with 9, we already know how to do it, and then we get this one, we get this one, we can cut the name them together, and that will be the results in BCD. Okay, that was a tricky one, the 59. I'm still thinking about it. It took long. Never mind. Get only studying physics and computer science. Maths are not that important, right? Great code. That looked like a 6. Great code. Great code is a binary code. In which consecutive values differ by only 1 bit. So this is useful in systems such as rotary encoders, because it reduces errors when moving between adjacent positions. Okay, let's try to have a visual representation of it. Let's do it in a new one. So we have decimal. Can be 1, 0, 1, 2, 3, 4, 5, 6, 7. Let's do binary. Let's try to make it more clear, otherwise it's gonna be really confusing. This one is a tricky one. I don't know if somewhere in the future we are meant to memorize all code system, or if some software or some systems will just allow us to be focused on just one, and just one could be, well, just one we could, by crazy repetition we could memorize it, but all of them, I don't know if someone knows all of them, or I don't know if someone with a lot of more experience than me will see this video. So if you have more experience than me and you're already into this world, you're already like a software engineering, by any casual you just see this video, just drop it in the comments if you are meant to memorize them all, or just one, or not even one, you just go and take the table every time you need it. I'm curious about it though. I don't know if you're meant to memorize them all. I could give it a try, at least one, but all of them, for example, right now this one is really tricky. Okay, let's move on. Binary. 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1. Okay, now in gray code. Zero, 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 0, 0, 1. Now it's 0, 11, 0, 1, 1, sorry, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 0, 0. Which is the loud one? I don't get it. because in the previously um, definition we saw that it only vary in one, right? Let's go back. I think it only vary in one. Code is separate if it counts. This is basically okay. We got here. Click on. Values differ by only one bit, but if it differs only by one bit, why in decimal position 7 it differs in 2 bits? Because what I'm thinking about is, let's check for example the first one that here it say like 1 0 1, and then in gray code is 0 1 1. Okay, 0 and 0 are the same, 1 and 1 are the same, and 0 and 1 are not the same. So this they differ by only one bit. Take another example. For example, this one is 1 0 1 and 1 1 1. 1 is equal than 1. 0 is different than 1. This one differs, but 1 is equal than 1. So the definition is right. But here we have 1 1 1 and 1 0 0. 1 is equal than 1, but these two are different. I didn't saw that when I was preparing the schedule for the call for the video, but they have to go through. Let's have a look. I cannot move on without knowing why this is happening. So the video is gonna be even longer, but we need to know why. Okay. Oh, I hope this is not gonna stop. If this is stop again, I'm gonna get crazy. It's so difficult to record the video today. Okay. Okay, if we do the 7, the 6 is 1 1 0 1 0 1, and 1 0 1, which is in gray code from 6 to 7, 1 0 1, the 1 repeat, the 0 repeat, and this one doesn't repeat. Okay, I was doing it wrong. I was thinking that from binary to gray code it differs by 1, but it was just casuality. It's not that it's differing 1 from binary to gray code. It's differing 1 all the time from gray code to gray code. I mean, from position 2, from 3, from 4, 5, 6. Okay, so yeah, in this case differ this one. In this case 0 is 0, 1 is 1, but 0 and 1 are not the same. Okay, so it's in here with it differs only by 1. That's why in here it will make no sense for me in the last one, because I was comparing this one with this one, but you have to compare this one with this one. Okay, now I get it. Okay, now it's kind of even easier to follow the table like this, because if you try to memorize it from here and compare it into here, that's a bit different. But knowing that it has to differ from here to here for the rotations. Okay, now makes more sense. Okay, we can move on. Hopefully this is still recording. Okay. Okay, normal binary may change multiple bits. For example, 3 is equal to 0, 1, 1. 4 is equal to 100. So 3 bits change. But in gray code, changes only 1 bit. So 3 is 0, 1, 0, and 4 is 1, 1, 0, which is only 1 bit different. Okay, we see samples in here. It's only 1 bit different. So gray code is not mainly about shorter numbers. It is about safer transitions between neighboring states. Okay, let's move on. ASCII. I'm not sure if they are called like this, but I'm gonna call them ASCII. I apologize if it's not like this. For me, it will be. So ASCII is an 8-bit character encoding used historically and still in some IBM mainframe environments. Okay, ASCII is important because it it reminds us the the binary patterns do not have universal meaning by themselves. The same bit pattern can represent different character, can represent different characters under different encoding systems. So ASCII became more common in modern systems. But FCD remains relevant in legacy environments. Okay. A file encoded in FCD may look wrong if a program tries to read it as ASCII or UTF-8. Okay. So same idea, a bit interpreted by code table ASCII table. It means not the same. Okay, this is this aesthetic table. Okay, so it's actually the code table that gives meaning to the bits. Okay. Okay, so we check this last table. Let me go through it. Maybe it's not yeah, let's do this table as the last table, and we finish with the number system based conversion and coding representation. Okay, coding representation comparison. Okay, let's put code. ASCII Unicode B C D gray code and ASCII. Not working. That wasn't that bad. So what it represents? It's basic English text and control characters. Global text and symbols. Decimal digits. Ordered states. Position. And text in IBM mainframe systems. Okay, main idea. These characters mapped to numeric codes. Okay. Universal code points for many languages. Each decimal digit gets 4 bits. Only 1 bit. Let's put it with one bit changes between neighbors. And legacy 8-bit character code. Okay, so with that we should have covered the number systems, base conversions, and coding representation. I think for the next video we will start with the booleans and logic gates. For now, that's okay.